Welcome to the deep dive. Today we're heading into some really interesting territory, maybe even mind-bending, but ultimately, pretty clarifying stuff from the world of calculus.
Yeah, we're taking a close look at section 1.6, shadows, from Dustin Potter's Calculus Unbound, specifically the shadows in galaxies part.
Right, and what's the goal here? What are we trying to unpack?
Well, our mission really is to understand how these things called infinitesimals and hyperreal numbers, which sound maybe a bit abstract, how they actually build a solid bridge to the real numbers, the ones we use every day.
Okay.
And this connection, it's not just some academic exercise. It's actually fundamental.
Yeah.
It's what makes calculus rigorous and work in the real world.
Makes sense. And I hear we're also pulling in some learning tips.
We are, because, let's be honest, this stuff can make your brain stretch a bit. So we'll grab some great strategies from Barbara Oakley's A Mind for Numbers to help make sense of it all.
Cool. So, a shortcut to understanding a key calculus idea, plus some tools for learning tough stuff in general.
Exactly. You get the concept, and you get ways to learn it better.
All right, let's dive in then. The word infinitesimal, we kind of think super, super small. But what does it really mean in calculus for two numbers to be infinitesimally close? Is it just really close?
That's the perfect starting question, because it's more specific than just really close. For a long time, mathematicians sort of waved their hands about getting infinitely close, and it caused some problems, some paradoxes. So Calculus Unbound introduces hyperreal numbers. We use the symbol or R for them. Think of them as an extension of the regular real numbers, R.
An extension.
Right. And when we say two hyperreals, let's call them A and B, are infinitesimally close. We write it as a simeq or a B. It means their difference, ABDMAOA, is actually an infinitesimal number.
Okay, hold on. An infinitesimal, it's not zero, but it's smaller than any positive real number. That still feels tricky. How does that fit on the number line I learned about?
It definitely stretches our standard picture of the number line. An infinitesimal is, it's a non-zero number. But its absolute value, how far it is from zero, is smaller than every single positive real number. Pick any positive real, like 0.000001 or even smaller. An infinitesimal is smaller than that.
Wow, okay.
It's hard to picture directly on the old number line. That's why Calculus Unbound uses a great visual metaphor. Think of an infinitesimal microscope.
A microscope?
Yeah. Zoom in on any real number, say the number 2. Instead of just seeing that single point, this microscope reveals like a whole cloud or halo of hyperreal numbers packed incredibly close to 2. They're all infinitesimally close to it.
Ah, I see. So it's not just one point, it's like a whole cluster.
Exactly. A cluster. It helps you imagine the hyperreal line as being way more dense, almost fuzzy, compared to the real line we usually think about.
That microscope idea helps. So infinitesimally close isn't just saying approximately equal. It's pointing to this whole hidden structure around each real number.
You got it. And that structure, that cloud, is what we formally call a halo.
A halo.
Okay, the halo of a number B, written HAB, is just the set containing all the hyperreal numbers that are infinitesimally close to B.
So how 2 would be all those hyperreals clustered around 2.
Precisely. Think of it maybe like, the slight blur you might see right at the edge of a really sharp photo if you zoom way, way in.
Yeah, kind of like a soft edge.
Right. That blur, that collection of points that are almost but not quite exactly on the edge, that's kind of like the halo. It's the collection of points infinitesimally close to the sharp edge of the real number.
Okay, that visual works. So does every real number get 1? Like, does 5 have a halo? Does 12 have a halo? Does pi have its own halo?
Yes, exactly. Every single real number, whether it's simple like 5 or rational like 12 or irrational like pi, each one has its own unique halo, its own distinct cloud of hyperreals surrounding it.
And are these halos, separate from each other, or do they overlap?
They are distinct. HAL2 and HAL-pi are completely separate sets. The real numbers act like anchors, each with its own little infinitesimal neighborhood around it. Got it. Okay, so we have real numbers, these hyperreals extending them, and halos clustering around the reals. What's next?
Well, this leads us straight to something really central, the shadow principle. It's theorem 1.6.2 in the book.
The shadow principle. Sounds important.
It is. It states that every finite hyperreal number casts exactly one real shadow.
Okay, finite hyperreal. What does that mean? Not infinite.
Yeah. Basically, just like our real numbers aren't infinitely large or small. So for any of these reasonable hyperreal numbers, let's call 1b, there is one and only one real number that is infinitesimally close to it. We call that real number the shadow of b, and we write it shb.
So B is hyperreal, maybe slightly off a real number, and B is the exact real number it's super close to.
Perfect. You can think of it like this equation. B equals shb plus,
Okay.
where B is the hyperreal, shb is its real shadow, and epsilon is that tiny infinitesimal difference between them.
Okay. And why is the shadow principle such a big deal? Because this is the bridge. This is how we connect the sort of abstract world of hyperreals and infinitesimals back to the solid, measurable, real numbers we use in science and engineering.
I see. Without it, the hyperreals are just out there.
Kind of, yeah. It'd be theoretically interesting. But the shadow principle gives us a rigorous way to get a real number answer from calculations involving infinitesimals. It makes the whole system practical. The book uses another nice analogy here. Shadow is like the crisp outline cast by a blurry object.
Oh, I like that. The hyperreal B is the blurry object, and its shadow is the sharp single real number it corresponds to.
Exactly.
This makes so much sense now. I remember reading earlier in Calculus Unbound, like section 1.3, about the old problem of finding the exact slope of a curve, say y by 2 at 2 and 4. You could get closer and closer, but it was always this fuzzy, how small is small enough problem.
The limit definition handles that, but it can be complex.
Yeah, and the text even said something like, to do that, we will need to invent new types of numbers, these hyperreals. And now the shadow principle seems to give a clean way to get that exact slope without the fuzziness.
You've absolutely nailed it. It provides a rigorous way to handle that infinitely small but not zero step. And the beauty is how well these shadows work with arithmetic.
How so?
Well, Theorem 1.6.3 shows that shadows behave just like you'd hope they would, following the familiar rules of real numbers.
Okay. Like what?
Like the shadow of a sum is the sum of the shadows, A plus C plus A as HE. Same for subtraction.
Simple enough. So basically, shadows behave algebraically just like real numbers do. You can distribute the Xi operation over all the standard arithmetic.
That's the key takeaway. It makes working with them very predictable. All your algebra skills still apply when dealing with shadows.
But okay, as we said, getting your head around hyperreals, halo shadows, it takes some mental effort. You mentioned learning strategies from Barbara Oakley.
Absolutely. And they're really helpful here. Oakley talks a lot about chunking.
Chunking, like breaking things down.
Sort of. It's more like binding pieces of information together through meaning, so they become one mental unit, one chunk. For today's stuff, you could form chunks, like first the idea of infinitesimal closeness, then the halo concept, then the shadow principle as the bridge, and finally, the properties of shadows.
So you build up these connected ideas.
Right. Once you have those chunks, your brain doesn't have to juggle all the tiny details separately. You think shadow principle and the related ideas, finite, hyperreal, unique real shadow, the B plus A equation kind of come along with it. It makes thinking more efficient.
Okay, that makes sense. Build mental building blocks. What else?
Another huge one is understanding focused versus diffuse thinking.
Focused and diffuse, like concentrating hard versus daydreaming.
Kind of. Focus mode is like the tight beam of a flashlight. It's when you're concentrating, working through steps, applying rules like factoring that polynomial. It's very precise, like a pinball machine with the bumpers close together, keeping thoughts on a narrow path. Diffuse mode is more relaxed, like the bumpers are far apart. Your thoughts wander more widely, making connections between different ideas. This happens when you step back, take a walk, shower, or even sleep. It's crucial for seeing the bigger picture like, that's why shadows are useful, or seeing how infinitesimals fit into the number system overall.
So you need both, not just intense focus.
Definitely. You often need to switch between them. If you're stuck on a problem focus mode, sometimes the best thing is to take a break and let your diffuse mode work in the background. You might come back with a fresh insight.
I like that. It gives you permission to step away sometimes.
It's actually essential. And that ties into the last point. Embrace befuddlement.
Embrace being confused.
Yeah.
That sounds counterintuitive.
It does. But Oakley and others like Kenneth Leopold, she quotes, point out that feeling confused is a totally normal part of learning something complex. It means your brain is grappling with new connections. Leopold apparently said, articulating your question is 80% of the battle. Often, just trying to figure out what exactly is confusing you helps you find the answer yourself. So don't feel bad if infinitesimals feel weird at first. It's a sign you're engaging with the material. Persist, switch thinking nodes, practice, and clarity will come.
That's actually quite encouraging. It's okay to be stuck for a bit.
It's more than okay. It's expected.
All right, so with these learning strategies in mind, let's connect these shadows back to the bigger picture. Where does this lead us in calculus?
It leads directly to the core concepts. Take the derivative. In Calculus Unbound section 2.1, you'll see it defined rigorously using shadows.
So the shadow is the derivative, essentially.
It's how we precisely get the derivative in this framework. It replaces the more complicated limit arguments for many standard functions. It's often much more intuitive.
And limits themselves and continuity.
Shadows give a really neat way to think about those, too.
Okay, so wrapping this up, these shadows aren't just some footnote. They seem absolutely central. They're the mechanism that makes this whole idea of infinitesimals rigorous and allows us to connect them back to the real-world numbers we need for calculations.
That's the perfect summary. They're the essential bridge. They make infinitesimal calculus work both mathematically sound and incredibly useful.
So maybe for you listening, take a second to think. Why is it so important to have this solid link? Why does connecting the abstract hyperreals to the concrete reals matter so much for understanding change, whether it's in physics or economics or anything else?
Yeah, reflect on that. And here's a final thought to chew on. If every real number we use is just the shadow of this vast, incredibly rich galaxy of hyperreal numbers clustered around it, how does that change how you think about numbers, about precision, maybe even about reality itself?
That is definitely something to think about, a whole galaxy hidden behind every number. All right, remember those learning strategies as you tackle these ideas, chunking, focus versus diffuse modes, and embracing the confusion. Thanks for joining us on this deep dive into shadows and galaxies. Keep exploring.